Okay, Jonathan, you want to start? Okay, so let's get started. I wanted to make a few announcements. The first announcement is that the lab 1 is supposed to be out today, and it will come out, but it will come out probably late in the evening. Okay, there's still some preparation going on for the lab. Okay, and I'll say something more about that in just a second. Second announcement is that there's also second homework supposed to come out today. That will also come out probably late in the evening as well. Okay, and then for next week, if you look at the schedule, there is supposed to be a guest lecture on cloud computing and data centers. So we will have a guest lecture. It will be a person who actually is a good expert on cloud who will come and give that lecture. Okay, so do come for that. That's next a week from today on Wednesday. Okay, Monday is a university holiday. Okay, it's President's Day, and Tuesday is supposed to be Monday's schedule, but we are not going to have a class on Tuesday. Okay, we had a makeup class last Friday because I was going to travel. So since I'm on travel, I won't be here. So we will not have the Tuesday class, which is technically a Monday schedule. Okay, so keep all of that in mind. I will update the class schedule to show that there will not be a class on Tuesday. It still shows a class because I was worried today would be a snow closure, but the university is open, so we are actually still one class ahead of schedule. So I can safely cancel the class on Tuesday as I had wanted to. Okay, so let me say a couple words about the lab before we go back to the lecture. So the first lab is going to be on remote procedure calls and threads. Okay, so you will essentially build a distributed application, okay, which will require you to use things like RPCs for the application components to communicate with one another. Okay, and you're supposed to ensure that the components are concurrent, which means that if there are two RPC calls from two components coming to a third component, it needs to handle them concurrently. Okay, so which also means you have to ensure that there is threading and concurrency for any data, rather synchronization for any data structures and so on. Okay, so you will learn client-server programming, or really distributed programming, not necessarily client-server. You'll learn about remote procedure calls. You'll learn about how to build concurrent systems. Okay, and a little bit about how to do measurements of your system to convince yourself that it works well and things of that sort. Okay, so that's the goal. We will be using GitHub Classroom for the project. So you will essentially develop your code on GitHub. Okay, GitHub is not where you go and the last day and turn in your code. We want to see your entire development history and check-ins and all of those things. Okay, and all of that instructions will be on the lab description page. Okay, so so this will be the first programming assignment. So we'll do this. I would think of this as a more low-level programming for distributed application. Okay, next time we'll build on this for lab 2, and you will program at an HTTP layer. We'll build a multi-tier application. Hopefully, you will even deploy it on the cloud. And then the last one, you will actually build a Docker version of the app with microservices and so on. So you will learn different ways to write distributed application. The last one is what you will often see today. What you are going to do in the first lab is really a very low level of programming. Okay, so that's the way you will get exposed to all layers of the stack in some sense as well. Okay, yes, question.
I know you said we could use different languages, but is there one that you recommend?
Okay, that's a good question. The lab is going to say something about this. So for this class, we have actually not enforced any choice of programming language traditionally. Okay, so you can do it in Java, C++, or Python. Okay, if you think you want to use some other esoteric language, at least check with us so that we know what you're doing and can advise you accordingly, because you will build on some of these ideas. So you don't want to pick something that will constrain you down the road. But if you stick to one of these three, that's a pretty safe bet. Okay, you can pick whichever one you're most comfortable with. That should be fine. Okay, so you actually get to decide what you write your code in. Is that good? Okay, so with that, let's get started. So the first module of slides is actually on server design issues. I actually covered this in the Friday makeup class. Okay, but there are two slides I didn't cover, so I'm going to go through those quickly. So we started talking about how do you design client server applications. I said servers actually have to be iterative process where the server application essentially an infinite loop where it's sitting and waiting for requests. As each request comes, it's going to process it. Okay, if it's concurrent, then each request is going to spawn a thread, and that thread is going to go process that request on behalf of the server, or rather on behalf of the client. Okay. Now, you have to deal with issues of which port number your client is going to listen on, how does the client know. When we talked about RPCs, we talked about a naming service where the server could register itself and so on. So those are good ways to design systems. You don't want to hard code this kind of thing into the client application, which says server runs on this IP address and this port number and things of that sort. So the more flexibility you have, the better. Should you need to hard code things, at least use a configuration file that is read at startup time. That way you can at least don't have to recompile the code. You can just change a config file and initiate your application that way. Okay? So these are things to keep in mind. Okay? I talked already about stateless and stateful servers even last time when I was talking about server push and client pull, so I won't dwell on that. I do want to talk a little bit about clustered applications or clustered servers. Okay, and this is a picture we will come back to when we talk about the World Wide Web. Okay, so this pictures actually show you ways to deploy multi-tiered web servers. We talked about multi-tier architectures a little while ago. Okay. This is just showing you a three-tier architecture where the client requests are coming in. The first tier is an HTTP server that's listening for HTTP requests. There's a dispatcher that is sending the request to the next tier, which is a cluster of replicated application servers. Okay, this is where the code for the application resides, and you'll see that in this case there are 6 of those servers sitting there servicing requests. Okay, this is just to scale the application up. Okay, and the third tier is essentially in this case a database tier, which is also replicated, as you'll see, but the degree of replication is different for different tiers. Okay, in one case there are 6 replicas, in another case there are 3 replicas, and so on and so forth. Okay, so when we come back to the web topic, we'll come back to this, revisit this just to help you understand more details of what is going on. At this point, all that you need to understand is whenever you have servers that process a high volume of requests, the server is often going to be replicated or clustered, okay, which means it runs on multiple machines. Okay, and then the requests have to be sent to one of those machines for processing. Okay, that's basically a clustered architecture. Okay. Now, what is shown in the second slide, not the second slide, rather the second figure here is how request processing can actually take place when you have a clustered server of this sort. So if you go back to the very first class, okay, we were talking about transparency, and we said that you can make a server be replication transparent, which means that the clients don't actually see that the server is clustered or replicated. They just see one node that you connect to. Okay, but then that node is going to deal with where that request gets processed and so on. Okay, so this slide shows you some details of what is going on. This is actually called essentially TCP splicing. So this is the front end node that that represents the entire cluster of servers. Okay, and then the client is actually going to connect to that node and send a request. Okay, and that's basically going to mean it establishes a TCP connection with that node. Okay, but your request is actually getting serviced by some other node, which is invisible to you. Okay, so you have not actually made a connection to the server that's actually going to process your request in this case. Okay, so what is going to happen instead is the switch will make another connection to the actual server that is going to process the request and forward the request to it. Okay, so now there are 2 TCP connections, one from the client to the front node and one from the front node to the actual server that's processing the request. Okay, and these 2 connections are essentially spliced, which means any request that comes on one connection is simply relayed onto the other, so it just the switch acts as an intermediary that's funneling packets back and forth. Okay, so this allows you to make things transparent to the end client. Okay, some networking details that you got to take care of for you to provide replication transparency. Yes, question there. Yes. Okay, so good question. What is being pointed out is if you see this picture, the request comes to the switch sends it to the server, but the response in this case at least is not coming back through the switch. Okay, it could have. It basically could have just come to the switch and the switch would have sent it to the server, but for latency reason you see that the server has actually sent the response directly to the client. And then the question is, if the client never established the request or a connection to the server, how is the server possibly sending a response back to the client? Okay? And the answer is actually it is spoofing the IP address of the switch. Okay? There's even more networking details than we need to go into. But when the server sends the reply, it actually sends the reply with the IP address of the switch with which the client actually has a connection. So this client doesn't know that this reply actually came from a third machine. Okay? This is to keep everything transparent. Okay? That more networking details, but that's what's going on. Yes, there's a question. Okay, question is how is the DNS configured for multiple servers? So DNS is a domain name service which allows you to translate the name of the server to its IP address. Okay, so if you have cnn.com, it will give you the IP address of that machine. Okay. So in this case, because you are replication transparent, the entire server, let's say the HTTP server, the URL of that server will simply point to that one switch. Those other replicas are transparent to the outside world, so they have internal IP addresses that are not exposed outside. Okay? You may have actual DNS level load balancing, which we'll get to as well, where the presence of those servers is visible to the client. In this case, it's invisible to the client. Okay? Okay. So more of this we'll come back to, but just keep in mind that servers can be clustered or replicated if you want to scale up the capacity. Okay? And then last, we had talked a little bit about the architecture of the server going from sequential servers, single threaded. Okay? While loop, which is one thread, just waits for a request, processes it, goes back, takes the next request, processes it, and so on. Okay? It's a very simple sequential server. Okay? Cannot deal with concurrency or does not have concurrency. Okay? And neither can it take advantage of multiple cores and so on. Okay? That's one architecture. That's the simplest server you can write. Okay? The server you probably would want to write for things like your lab is a concurrent server, okay? Where you still have a loop, but whenever you get a request, you might spawn off a new thread, okay? And then have the thread service that request. Or you have a pre-spawned pool of threads. When the request comes, you hand it over to a thread. Okay? So you have to do some thread management, but now you get concurrency, which means multiple requests can be serviced at the same time and so on. Okay? So between those two models, there are many variants of it. Okay, so the concurrent is not necessarily just a thread based, you can have process based concurrency as well, which simply says that you have multiple processes and then there's a master process, and the master process is receiving the request and then sending it to one of the slave processes. Okay, so you are now getting concurrency at a process level. Okay, and you can do the same thing as a thread level where there's a master thread. Okay, so that's thread based model. Okay, thread-based concurrency. You have master thread and a set of slave threads, and the master thread listens for requests and sends it off to the slave thread. Okay, so you have both of those models, both give concurrency. Okay. And then in the sequential model, if you want to actually emulate some benefits of concurrency, you are going to make that event-based or asynchronous. You can make the server asynchronous, still a single thread. Okay. However, now you are doing event-based, or you have to have event handler so that whenever there's an event, you jump to the event handler and handle that event by writing code for that event handler and so on. Okay, this allows you to take a sequential model and make it look like you get benefits of concurrency without using threads. Okay, but it requires that you do something called asynchronous programming. No blocking calls at all. All calls have to be non-blocking so you can continue to execute, never block on anything. Okay, that's the most kind of complex kind of server to write. And the other thing I had mentioned was, if you think about efficiency, which is the last question here. Okay, so typically you have to say efficiency with respect to what. Okay, so if you think about context switch overheads as a measure of efficiency, okay, then you will see that process based, okay, will have incur context switch overheads when you switch between processes, okay, of that same server. Okay, and then thread based will be less. Will have imposed less overheads because of switching between threads of that server rather than processes. Process context switches are more expensive than thread based. Okay? And then when you come to event based, there is no context switching at all because everything is happening inside a single process. Okay. So the context switch overhead is gone. If that process is continuously busy and the only one on that processor, it will run continuously without any context switch overhead. Okay. So in terms of efficiencies of context switch overheads, event-based architectures win. Okay. They are the most efficient architectures for writing server applications. Okay. Now if you think of efficiency from other perspectives, such as taking advantage of multiple cores, then the picture changes a little bit. Okay, neither sequential nor event based can take advantage of cores because they are single threaded, both of them. Okay, only says a traditional process. Okay. Both of these latter two architectures can take advantage of concurrency because they are either multiple processes or threads. Okay, assuming you use kernel level threads, of course. Okay. Now you can also have hybrid architectures where you combine the thread and event based. You have a thread per core, and then that thread is doing event based. Lot more complicated architectures that we don't want to go into here. Okay, but that's the simple way to think about efficiencies of these. Okay, just repeating this so that you keep this in mind. You will have to pick one of these for your lab as well. Okay, that is why I wanted to repeat some of this. Any questions here? Okay. So I'm just going to go through this quickly. How do you scale your server? You can buy more hardware, buy a bigger machine. You can replicate that server on multiple machines. That was the clustered architecture. You can make your algorithm or data distributed. Distributed is not the same as replicated. You should understand the difference between the two. Distributed just says you take a task and split it into subtasks, and those subtasks run on multiple machines. Okay. Replicated means you take the entire code and just run it on multiple machines, and you partition the workload requests. Okay. So you can distribute, you can replicate, you can cache, okay, or you can essentially ship code instead of data, which we'll get to today. That I don't want to get into that at this point. Okay. All right. So with that, your question, yes, please.
If you do distribute the algorithm, for example, wouldn't it still have the same problem like if you're not replicating it?
Okay. Question is, if you could distribute your algorithm across machines, would it not have scalability problem of not being replicated? That's your question, right? Okay. So yes, you want to answer it? Okay, you had a different question. Okay.
What is shipping code?
Okay, I'll come to that. Let me answer that, then I'm going to talk about that. Okay. Okay. So let's get to this difference between distribution and replication. So distributed simply says I have a large program, okay, or a server application. I partition it into smaller tasks, and each task runs on, or some subsets of tasks run on multiple machines. Okay, you can only scale that so much. If you had 1,000 machines, you can't take your code and say I'm going to make 1,000 little pieces and each thing runs on a different machine. Okay? But if you have 2 machines, it is entirely conceivable that you can take your application, split it into 2 pieces, and piece 1 runs here, does some part of the application, and piece 2 runs there. That would be very similar to if you had the entire application, you just ran it or replicated it on 2 machines and then just split the workload. Right? So you can scale to some degree by making things distributed. Okay, and then you can also scale by making a replicated application. You can, of course, do both. There's nothing that says that you have to pick one or the other. In fact, multi-tier clustered servers are an example of both, because you are replicating a tier and you're distributing the application functionality across tiers. Okay, the tiers actually are distribution. You said HTTP processing happens here, app server is sitting here, database processing is happening here. That's distribution. Okay? And then you replicated each of those pieces as well. Okay? So you can scale using either of those 2 methods and combine them as well. Okay? Now coming back to your question, what does shipping code instead of data means? Basically the idea is, rather than you sending data over to a computation, the code is actually going to come to where the computation is and execute, and the best example is going to be in the next few slides. Okay, that's what I said. I'm going to hold off on that, and you will understand what that means in just a few slides. Okay, so we'll talk now about migration. Okay, we'll start with the first module, which is going to be on code and process migration, and we'll end with the last module on virtual machine migration. Okay, so let me start with what does migration entail and how does it work at a very high level. So we have encountered process migration already. When we are talking about distributed scheduling, okay, we said maybe there's a process running on a machine. machine gets overloaded. Can we suspend that process, move it somewhere and continue execution? And we said that requires process migration to be implemented. You're taking a process, an active process, suspending it and migrating it somewhere else. Okay? It's complicated to do, but there are operating systems that actually provide that support. Okay? And there are many other reasons to do it, but that's where we have encountered it so far. Okay? Here we are going to delve a little deeper and look at this whole issue of migrating code or processes. Okay? So first is we want to distinguish between what we call code migration and process migration. Okay? Code migration simply means that you are going to take the program, move it to the machine where you want to run it, and then start a process on that machine. Okay? That could be I just took a binary, I copied it onto another machine and I started it, or even simpler, you write a Python script, you just transfer the Python script and just start it on that machine. Okay? That's an example of code migration. Okay? Process migration says that it's already an executing program, it's running in memory, it's resident in memory, it's running on that machine. You're going to suspend that, move all of the memory contents over, register contents over, initiate a new process and start executing or resume executing it somewhere. Okay? That's process migration. Okay? So we want to distinguish between the two. Okay? Process migration we'll call also refer to as strong mobility. Code migration we are going to refer to as weak mobility. And there are many examples of both code and process migration that go beyond what we have looked at. Okay? Let me give you some other examples of code migration. Okay? So if you fill a form, web form and you submit it, okay? That's an example of code migration, because that's basically going to send some code over to the with the data over to the server process and is going to process it. Okay? If you actually have Flash or Java applets running in your browser, that's an example of code migration. Okay? You downloaded some Flash code and it's running in a Flash interpreter. You downloaded a Java applet, it's running in your browser. Okay? Example of code migration. That code is now running inside the browser process. Okay? Not a new process, but still an example of code migration. Okay? Very simple things like you do a web search. Okay? A web search is nothing but a query. Okay? A query is a program. Okay? You're essentially sending that query over to a web search engine, and that is going to execute that query and send back a result. Okay? Even something as simple as that actually falls under the category of code migration. Okay? Because you basically sent off a query over a network to another machine and it executed there. Okay? That's an example of code migration as well. Okay? Now there are many other examples of this of strong and weak mobility. Okay, your question is.
I didn't quite follow the last example you gave about why a search query would be considered as code migration.
Okay, question is why is a search query an example of code migration? Okay, first is code is same as a program. Okay, so first you have to believe that a query is actually a program. So a SQL query is a program. Okay. Now, when you are expressing a search query in a search box of a browser, you just type some keywords, but that's essentially a query saying find me all documents with these keywords in it. Okay? That's a query. Okay? Now, if you hit submit, that query is being sent off to another machine. So you transferred a code, which is the query, over to another machine and executed that. So your code has migrated to the server and got executed at the server. It would be no different if you actually wrote a SQL script and sent it off to a remote database for execution. Okay, that's also an example of code migration. Yes, question.
On process migration, if you save the process immediately, how do you take care of things like the state of the process?
Okay, question is in process migration, if you suspended the process midway, how do you take care of the state? Okay, so that's your question. So state, in this case, the state of the process are the memory contents of the process. There are the register values of the process. There could also be other resources you're accessing like files and so on, okay, which we have not talked about. But the memory state of the process is straightforward because it's just the memory contents of the process. You can simply save it to disk, resume it, or write it somewhere else and so on. Okay? So that's not as big a problem. In fact, if you ever used debuggers, they do this all the time. Okay, so they essentially can take your memory contents, write it, that's called a core file, and then you can resume execution or step through execution and so on and so forth. Okay, so that's how they would take care of that. Yes. Okay, question is, does the migration have to be between a client and a server, or can it be between a cluster of servers? So migration is independent of where the code is and where it goes, or where the process is, where it goes. Okay, it can go from a client to a server. We'll see it can also go from a server to a client. It can go from one machine to another. That's part of a cluster. So we are not limiting migration to just a client server application, or just saying it goes from client to server. Okay, it basically you have two machines. Forget whether they're client or server. The code of the process resides on one, and you're migrating it to another. That's all that matters. Okay. Yes. Yes. Why does it improve parallelism? Okay, so that's actually referring to agent-based search as opposed to web search. So we won't go into too many details there, but the point that you want to make there is your server is essentially a much larger resource that you can send multiple requests to. And so if you essentially send all of that requests over, you can get benefit of a larger cluster. That is, I think, what it was trying to say. Okay? I did not want to go into the agent-based approaches because we kind of removed that material from the course at this point. Okay, we did have multi-agents here at one point. Any other questions? Okay. So last thing I wanted to mention is another example of code migrations are things like, even things like Docker containers that you use is an example of code migration. You have a repository which has some images. There could be Docker images. That example actually tells you about a driver repository, device driver repository. Okay? So your machine needs something. It can download a driver on demand, install it, and run it. That's an example of code migrating from a repository to a server or a client and executing there. Or you could do the same thing with Docker. Okay, if you want to run a certain application, you can download a Docker image and just start running it. Okay, so many different examples of code migration. Yes.
Sorry, I have one more question from the previous slide. Why is process migration considered strong mobility and code migration?
Okay, question is why is process migration considered strong and code migration considered weak? That's just terminology. Okay, it doesn't mean that strong means something better than weak. Okay, that's just a term. You will see the same term used in papers saying strong mobility. That's a synonym for process migration. If you see weak mobility, that means a synonym for code migration.
My point is more like, what is the motivation for using these names?
Okay, what's the motivation for calling something strong or weak? That's a different question altogether. That's why did they name that strong or weak? I would have to think about that. I don't actually know. But that is what researchers use. Okay, we are going to actually just call it process and code because that's more explicit what is migrating. When you say strong or weak, you don't actually know what is going on under it. But they are just a synonym just for you to know that these terms exist. Okay, yes.
Out of curiosity, could it be because process migration implies that you do code migration by moving the code with the process?
Okay, so the point being made is process migration does involve code migration, and so process migration is a superset of code migration, right? Because you are moving the code and you are moving the state of the process. There are two things in a process. There's the code and there's actually the memory state. So in process migration, you move both. In code migration, you're only moving code and the process or the state is set up later. Now, that is indeed true, but if you think that makes it stronger, then sure, right? Okay, any other question? Yes. Okay, so downloading demand, drivers on demand, downloading Docker containers, all examples of code migration. Okay, now let's take a look at the migration in a little more detail. Okay, so as I just mentioned, a process essentially consists of the code. Okay, that's basically in this case, it's going to be executable code, not necessarily source code. And it's going to include things like your stack segment, heap segment, registers. That's all the state of that process, the data of that process, okay, as it resides in memory. Of course, the code also resides in memory, but that's a separate issue. Okay? So when you say process, we essentially mean the memory state of the process, which will include the code segment of that process, and it will include things like the heap segment and the stack segment and any other resource segment if the process is accessing other resources like files. Okay? That is the state of that process. Okay? If you want to move that process from machine 1 to machine 2, all of those things actually have to move over. Okay. So the typical way is you might suspend the state, because if you don't and it continues to execute, the state will keep changing. So if you send some state and it's already changed, then what you have on the new machine is old. Okay. So typically you will suspend the state, take all of those segments, transfer them over, initiate a new process, move the registers as well. Okay. The registers will have things like the program counter, which says what is the next instruction that the process was going to execute prior to suspension. So you will essentially create a memory image of whatever was on the old machine on the new machine, okay, as far as that process is concerned. Okay. And then you will execute, resume execution, so it will just continue executing from where it left off. Okay. That's a very simple, sort of a little more toned down version of what process migration entails, but there are lots of complications that we got to deal with. Okay. And they are all actually related to what are the resources that the process is actually accessing when you move it. So if the process has open files, okay, you move that process over, the files have not moved, they're still on the old machine. Okay. So if it now tries to write to a file or read from a file, it's going to get an error. Okay. Unless you move the file or somehow you make that file accessible over a network. Okay. Files can be made accessible over a network. You just need to use a network file system or a distributed file system. Okay. That's possible to handle. Okay. What about if you have open network connections? Okay. That's a much harder problem, because if you have open connections to other machines or other applications, you just move that process over, those connections will no longer function, because network connections are tied to the IP address of the machine, not just the process. Okay, if you move the process, the IP address of the old machine has not moved over. Okay, so that's going to cause some problems. Yes,
So
question.
in one of the previous slides you mentioned when there was a question that the IP address could just be spoofed from the switch to the server. Couldn't something similar be done to take care of this problem?
Okay, question is, could you spoof the IP address of the machine? So first of all, you don't want multiple machines to actually use real IP addresses and communicate, because the routers will not know which machine has that IP address. So when you do spoofing, you have to be very careful of what you're doing. Okay? We'll talk about virtual machine migration, where we'll see how to solve that problem. Okay? How to make the IP address problem go away, because typically IP addresses are assigned to machines, not to processes. So when you move a process, okay, the network connection is tied to an IP address. So that's the problem you got to deal with. Okay? So those are all issues that you have to deal with process migration. With code migration, you don't have any of those issues. Okay? You just want to make sure that whatever code you are moving has the necessary infrastructure on the other machine to execute. If you moved a Python script, Python better be installed, otherwise your code will not run. Okay? If you moved a Java program, JVM better be installed. Beyond that, or if it's a C program, there should be C libraries. Beyond that, there are no other issues. Okay? So long as you have the right libraries or the runtime installed, you can just move the code and execute it there. Okay? Much simpler problem to deal with than if you had process migration. Okay? Now, depending on which machine initiates the migration, okay, you can have either of these, process or code migration, be sender or receiver initiated. Okay? So essentially there are two machines. There's a sender machine, which is where the code used to reside, and there's the receiver machine, or the process used to reside, which is the one where the code or the process will execute after migration. Okay? Now depending on which of the two initiated it, your sender or receiver initiated, and there are examples of this as well. Okay? So the example where we talked about web searches and database queries, they are all sender initiated. There's a sender machine, you write a query, you type your keywords, you hit submit, okay, and then the code is going to the receiver. Okay, so sender initiated the migration, then the migration causes the code to go to the receiver and execute them. Okay. Now, if you have something like a browser that is downloading a Java applet or a Flash application from a server, that's going to be receiver initiated. Okay, because the server is the one that decides that you got to, or not the server, the browser is the one that decides that it wants the code and then fetches it and runs it. Okay, so you have examples of both sender or receiver initiated migration. And then the last thing to keep in mind is, after the migration, how is that code or process actually going to execute? Okay. So if you have code migration, you can start a new process. If you have, let's send a Python script, start a new Python interpreter and you just start executing it. Okay? Or if you have something like Flash or Java applets, they're actually going to run inside a current process, which is the browser process. So the code is executing, but you're not starting a new process. Okay? So either you start a process or you use an existing process to execute your code. Okay? In process migration, you almost always have to start a new process. You can't take a process and start execute it inside another process. Okay? Unless it's something like a JVM, that's a different problem. Okay? So that in that case, you will start a new process. So if you take all of these things we talked about, you get this essentially all possible combinations where you say the mobility mechanism could be process migration or code migration. For each of this, you can have the sender initiated or the receiver initiated. Okay, and then for each of those, you're going to execute within a target process, execute in a new process. I didn't mention the difference between migrate process and clone process. Okay, migrate process is what I just mentioned, which is essentially you're going to migrate, move that entire process. Clone process simply means you make a copy, and then that copy starts executing. Okay, it's the difference between moving a file and copying a file in a directory. Okay, when you move a file, you just actually move it over. When you copy a file, you make a copy or clone that file and create a second copy. Okay, so when you have, you can actually clone a process where you have the old process and then you make a clone of it. The old process doesn't go away. Okay? When you migrate it, the old process actually goes away and the new process executes. Okay? That's the difference. But in both of those two cases, the process, there's a new process that has gotten created. Okay? Yes. Okay, where would you do this cloning? There are operating systems that actually support cloning features. Okay, so if you wanted to do that, use that feature, you make a clone of your process on it's called remote cloning. You make a remote clone of your process so that you basically have a replica of that process on another. It's an easy way to replicate the process on a second machine.
Some kind of fault tolerance.
So you could use it for fault tolerance as well. I think that was some of the reasons why they introduced cloning features. Okay? But you're cloning files, no, I mean cloning processes, not files. That's something you want to keep in mind. Question? So question is, what happens to the old copy when you clone a process? When you clone a process, you just create a second process. Okay? Both copies continue to run. Okay? Yes. So I mean the simplest example on a single machine I could give you is a fork of a process. When you fork a process, that's a local clone. Okay, fork is a system call for those of you who don't know. Fork is a system call that just says create a child process which is a mirror image of the parent process. Okay? So fork is essentially a local clone. Okay? Now think of a distributed fork that does essentially that but puts that process on a different machine. Okay? So just as in a fork, the parent and the child continue to run, even in a remote clone, parent and the child will continue to run. Okay? But you migrated the entire process state in order to run it on a different machine. Any other questions? Okay, so that's migration. We'll talk about resources, then we'll move on to virtual machine migration. Okay, so the biggest problem in making migration work has always been what do you do with the resources the processes are actually accessing? What happens to the resources? Okay, that is where things really get complicated. Okay, you can have all kinds of resources. You can have files. Okay? You can have network sockets. You can have hardware resources. Maybe you are printing. Maybe you are writing to a USB disk on a machine. If you just move the process, what happens to all of these resources? How do they continue to get access, or do they continue to get access? Okay? So there are a number of different approaches you can use. Okay? And those are actually all mentioned here. But at a very high level, the options you have are make that old resource, not the old resource, make that resource on the old machine accessible over the network. Okay? So process has moved, but it can continue to access that resource over a network. This you could do for a file. Okay? You can just essentially use NFS to share that file so you can continue to get access to the file. Okay? So make that resource accessible over a network is one option. Okay? Move that resource is another option. Okay? Why couldn't you have moved that file over? You could potentially do that as well. Okay? So resources can move with the process. Okay? Resources can become accessible to the process remotely. Okay? Or you can substitute that resource with another equivalent resource. Okay? Suppose you are trying to access a printer. Okay? If the new machine has access to a printer, does it really matter if it prints to that other printer? It should be okay. Okay? Or if you wanted to access some libraries, okay? The same libraries are present, that's a dependency. You could just use the local. You just substituted an identical library that's present on another machine. Okay? So you can substitute, you can move, you can of course make a copy and still have another copy of the resource, or you can provide remote access. These are all the options we have at our disposal to make migration work with resources. Okay? And depending on what the application needs, different options are going to be feasible or not feasible. Okay? So that is what this slide is trying to talk about, saying how do resources migrate, and that depends on what is called the resource to process binding. Okay? What is the nature of the binding between the process and the resource? Okay, so there are three kinds. Okay? If you are binding by identifier, that means that's a hard binding. Okay? You are trying to access a very specific resource that is not substitutable. Okay? So an example is a website. Okay? A URL for website is a hard binding. You can't just substitute one URL for some other random URL. That does not work because the URL says you are accessing a particular object on a particular machine. Okay? That's basically a hard binding. Okay? Then a slightly weaker binding is what we call by value. Okay? Examples are libraries. I need to access libc. I need JVM. So long as the same kind of library with that name exists, you are okay. Okay? So that's a resource you can substitute with another resource. The binding has actually gotten weaker. Okay? And the least strict type of binding is by type, which essentially says things like printers. It doesn't mean that it has to be an HP printer of model XYZ on that other machine. Any printer will do. Okay? But for libraries, the binding is hard. You can't take JVM 1.2 and say you can run on JVM 1.0. It may not work. You at least need to match version numbers and all of those things. Okay? So here you have the weakest binding, which means you have the most flexibility in what you can do when resources move. There you have the least flexibility because you are accessing a certain type of resource that you can't just substitute with something else. Okay? So depending on how strict the binding is, what options you have when you migrate will change. And we'll talk about how you will do this in just a moment. Okay? And then the second is, if you are going to consider moving that resource or copying the resource, you got to consider the cost of doing it. Okay? So this is what is called attachment. So first, are the resources tied to machines or not? That's the first thing you have to ask. So maybe files are not tied to a machine. You can move the file over. Okay? A printer is not something you are going to move. Okay, is actually connected to a machine. It's not going to move by itself, at least. You might have to move it physically, something you would probably not do just because you're migrating a process. Okay? So unattached resources says there is no dependency. You can move it. Fastened resources say that there is not a dependency, but the cost of moving is high. Okay? Large files, large databases are example. Yes, you can copy it, but do you want to pay the price of copying 1 gigabyte of data or 10 gigabytes of data? Okay? And then the last one is fixed resources. These resources can't move at all. Okay? That's like a hardware that's connected to the machine and socket connections that are tied to the machine because the IP address belongs to the machine. Okay? So here, as we go down from unattached to fixed, it gets harder to move the resource, or more expensive to move the resource, or not at all. Okay? So you are going to now have all these combinations of what kind of binding you have with the resource and how hard is it to move that resource. Okay? Depending on this, you're going to get many different choices. And here's a table that takes all of those, and there's every possible choice. I'm not going to actually talk about every possible entry in that table, but I'll give you a sense of what is happening. Okay? So essentially, depending on the binding, okay, if the binding is tight, then you essentially have to say that I will provide remote access. Okay? If the binding is weaker, then you can say I can either copy the resource, move the resource, or essentially rebind that resource, substitute that resource with something else. Okay? So let's take a few examples so you get the sense of what kinds of options you have when you're migrating a process. Okay, so let's say it's the binding is by identifier, and it's a fixed resource, which means it cannot move. So you want to access a specific resource, no other resource, and that resource cannot move. It is tied to that machine that the process was running on. So your option here is what is called GR, that simply says establish global system-wide reference. That's just a fancy term for saying access it over a network. Okay, you can't move the resource. Only thing you can do is provide access to that resource over a network. Okay, so that's one example. Okay, so here let's take another example. So it's a tight binding, but you have fastened resources, which means it can move. So you can still provide remote access, but should you want to pay the price of moving it, you could move it. Okay, so it's that resource that has to move. Nothing else can move, but the cost of doing it is high. So ideally, you might want to just say, let's provide remote access through a system-wide reference. Okay. Now let's actually take some weak binding examples, saying you bind by type. Okay, if you bind by type, that means that there is really no dependency. So long as you have a suitable replacement resource on the new machine, you can just substitute. Okay. So you will see that rebind is always an option. Rebind just substitute. Okay. So here you can have substituted one Java library with another and so on. So you'll see, regardless of whether fixed or not, you can actually substitute that resource. One printer can be substituted with another printer. Both are fixed resources, but that's acceptable. Okay. Or you can substitute one Python interpreter with another one on the other machine, so long as they are the same versions of Python and so on. Is this clear what I'm saying? Okay. So this is not a technique. This is simply a way to think about how do you deal with resources. Any process migration system has to actually pick options from this table and say, this is what we are actually going to implement. Okay. So it's going to depend on, are the processes actually going to access resources? Are they compute-bound processes? What kinds of resources are we going to support? Should we support everything, or should we say only these kinds of resources we will support? Otherwise, you are out of luck. You can't migrate that process. Okay. So depending on how you make those design choices, you will get a particular system with a particular way of migrating processes and providing access to resources it accesses. Okay. This is just a way to think about what options you have, under what scenarios you can do what things. Okay. Any questions here? Yes. Okay. Question is, would you want to do checkpointing and write-ahead log instead of doing migration? So actually you mean checkpoint and restart, which is just a way of suspending the process and restarting it. Okay. Checkpoint is just a way to say, take the memory state of the process, write it out to disk. That's what's called a checkpoint. Okay. There are many other meanings of checkpoint, but in this context, that's what it means. And then restart essentially says, take a checkpointed file, load it in memory, potential on a different machine, okay, and then just resume execution. Okay. So checkpoint restart is essentially a way to implement process migration. Because typically what you will do is you'll write it to disk and resume execution on another machine. You could have just done a direct memory to memory transfer as well. Okay. That's also possible. But the more standard way to do this is checkpoint and restart. Okay. So this is just essentially a way to implement process migration, not an alternative to process migration. Okay. We will come back to checkpointing when we do fault tolerance. Okay. All of this we will look at because it is a broader problem of how do you deal with failures as well as process migration and all of that. Okay. Yes, question in the back. Okay. Okay. So the last point I want to make here is, how are you going to migrate if the machines are heterogeneous? Okay. Our implicit assumption, okay, which so far has been the source machine and target machine are actually this homogeneous machine, same OS, same architecture, everything is the same. Okay, so all you got to do is move the memory state and it will just run. Okay. What if one machine was Linux, another one was Windows? What if one was Intel, another one was ARM? Would this even be possible? Okay. Short answer is no, but that doesn't prevent people from trying interesting things. Okay, because by default you can't just take an executable from Linux and run it on Windows. It's not going to run unless you have something else to make it work, or one CPU architecture to the other. Okay, the assembly instructions won't work on the other one. Okay. But having said that, there have been efforts to saying maybe we can think about ways to do this. This is just one example from the book that shows you how people have done it. So first of all, this was weak mobility. This is not a problem. Weak mobility will work across architectures because you're just migrating code. So long as interpreted code like Python, what do you care? Okay. If it's Python that you're moving from a Linux to Windows, if there's Python, it will run that code. Okay? Of course, if it's a binary, it's not going to run. You can't compile code on Linux and then copy that executable and run. In that case, code migration will also not work, let alone process migration. Okay? So if you have interpreted code, that's not a big problem. Okay? If you have executables or your processes that are actually executing, that's a bigger problem. Okay? So what could you do? If it is just an executable, you can recompile it, create a new binary so long as your source code, and move that code over and execute. Okay? Requires recompilation. If you had a process, okay, as is shown here, there's a much more complicated thing you have to do, which is, first of all, the code segment cannot just transfer over on a different platform. It has to be recompiled. Okay? The data has to be moved over and the appropriate translations have to be done. Okay? Because maybe one machine was little Indian, the other was big Indian. You can't just move the code and expect it to work. So there are a lot more translation that has to do in addition to simple data copying. Okay? And if you do all of that and get it right, perhaps your code will work across heterogeneous machines under some limited circumstances. Okay? By and large, it won't work because this is just not something that's easy to do, because you might have pointers and all kinds of things. Just recompiling is not going to make it work. Okay? Now, having said all of that, okay, there's a pretty common case where this happens all the time, which is Java. Right? Because Java code runs on a JVM. Okay? That's an abstract machine, virtual machine that is identical across any platform. So if you are talking about Java code, then migrating across heterogeneous platform is not a problem, because all JVMs give the same abstraction, even though one may be running on Linux, one may be running on Windows. It doesn't matter. Okay, because a JVM is an abstract specification of what a machine looks like. It's the same across any architecture. The code is portable. So your process can actually move from one JVM to the other. So long as the same JVM, the platform is the same, you can actually move it from one OS to the other and so on. Okay? So that is actually an example of where you can make this work in a heterogeneous setting fairly easily. If you're talking about compiled code, okay, that's a much bigger problem. Okay? It's not very easy to do. This question.
Require like the JVM itself to export its like internal data structure that got migrated onto this machine, so it happened at like the JVM level as well.
Yeah. So question is, how can you do this at the JVM level and the OS level? We are actually talking in this case about doing it at the JVM level. You can do things like serialize, deserialize, and just restart your process somewhere else and whatnot. So there are lots of functionality to implement this kind of thing, okay, if you wanted to. Okay, any other questions? Okay. So having said all of this, now we will actually talk about migration in using virtual machines, where a lot of these problems actually go away. Okay? You can migrate not only process, you can migrate an entire OS with all of its processes. Okay? It doesn't matter whether the processes communicate, don't communicate. You can migrate the disk, you can migrate even IP addresses, as we will see. Okay? So we'll talk for the next 20 or so minutes about virtual machine migration. Okay. So first of all, before we talk about virtual machine migration, we should ask, why should we even consider migrating a virtual machine? Okay, what does it mean to migrate a virtual machine? Okay, so consider a case where maybe you have a type 1 hypervisor. Okay, this is a VM running on a server. Okay, maybe the virtual machine gets overloaded. Okay, there's let's say running a web server. Okay, web server gets lots of requests, gets overloaded. Okay. There may not be physical resources on that machine to service all the requests that are coming in. Okay. One thing you could possibly do is just take that virtual machine and simply migrate it to a bigger server. Okay. Now you have more hardware on the other server, more RAM perhaps, or more cores. Now your VM can service more requests. Okay. That's one example. Okay. Another example is you might have 3 VMs running on one server, 2 VMs running on another server, okay, and then maybe the first server gets overloaded because all 3 VMs start doing computation. Second server may be underutilized because its VMs are not doing much. Okay. So now you can use virtual machine migration to do load balancing, where you can take one of those VMs and move it over. Okay. So there are many examples of this sort which have basically motivated the need to implement virtual machine migration. If you have a hypervisor, okay, that is used widely, it's fairly typical for it to also support VM migration. Okay, so Linux hypervisors that use things like KVM support it, VMware supports this. You can essentially take a VM and move it from one machine to another. Okay. Now the interesting thing about virtual machine migration, which is different from process migration, is that you can do it in what is called live. Okay, which means you are not going to suspend the VM, move it over and restart it. Just as we said, if you want to migrate a process, first thing you got to do is suspend it, meaning it's not going to get scheduled, its memory is not going to change anymore because it's not executing, it's just sitting in memory. Then you copy the memory and then you execute. Okay. For VMs, we are not going to do that. We are going to let it run. Okay, it's going to continue to execute as if nothing has happened, and you migrated it, and after a while it will magically start running on the other machine with no downtime at all. Applications that are running inside the VM won't even know that they have moved to a different physical server. Okay. First of all, they don't even know that they are running on a virtual machine. Okay. But when you move it in this way, they don't know that they have moved over. So all of this is happening while applications continue to run. Okay. This is actually a powerful approach because you can move applications live without any downtime. Okay. All this load balancing can happen without any downtime at all. Okay. So this is why this has become very popular in virtualized systems, and there has been lots of work on how do you move, when do you move, and so on. Okay. Now, as I will show you, there are two techniques we will talk about on migrating virtual machines. One is called pre-copy migration, the other one is called post-copy migration. Both of them will move the VM live. Okay. By VM, I mean the operating system will move. Okay. All the processes inside the operating system will move. Neither the OS nor the processes actually know that they have moved to a new machine. Okay. So they will not see any downtime, everything will just move over. Okay. So here's a set of steps that you are going to execute in order for you to move a VM. Here's a small picture that shows what's happening. Right. So here that's your physical server. That blue box there is a virtual machine running on that physical server. There may be many VMs running, only one is shown. Okay. And our goal is to take this blue VM, okay, and move it to machine B, okay, while it is executing on machine A without any stopping of applications or the OS. Okay. How would you do this? That's one question. Okay. So first of all, we are going to ignore disks and files. We are only going to think about memory. Then I'll tell you a little bit about how you can deal with files and whatnot. Okay. So here is how you are going to do it. Okay. This VM essentially resides in memory. Okay. All the OS's processes all reside in the RAM that has been allocated by the hypervisor to that virtual machine. Okay. So let's assume that the blue box essentially represents the RAM allocated to that VM. Okay. You are simply going to take, RAM is just a collection of pages. Okay. So let's say there are n pages that are assigned to that VM, okay, in its RAM. Okay. So you are simply going to transfer those pages in sequence. Okay. We'll take page 1, move it over, copy it over, page 2, copy it over, page 3, and so on. So you'll just essentially go from page 1 through n and just copy all of those pages over. Okay. Once you have done this, okay, you have n pages on the new machine, which is machine B. Okay. You have n pages on the old machine, machine A. Okay. But since the OS is continuing to execute, processes are continuing to execute, some of the pages have changed after you sent them. Okay. Because maybe you wrote to memory, maybe you started a new process. Okay. So essentially some of the pages now on machine B are out of date with whatever is on machine A. Not all the pages, only some would have changed, hopefully. Okay. So you are going to iterate. You are going to track while you are copying over which pages are changing. Okay. In particular, those two red pages that you have seen are essentially have changed after you transferred the first round of pages. Okay. So in second round, you are only going to transfer what is called the delta, only things that have changed since you sent them over. Okay. Presumably the delta is smaller than the entire memory content. Okay. So your second round, you will send only the delta. Presumably it will take you less time to send the delta than it took you to send the first n pages because you are transferring less data over the same network. Okay. Since it's taking you less time, the same thing is going to happen. Then more memory is going to change. Okay. But presumably because now you are looking at how much changed in the time it took you to send the fewer pages, less memory would have changed. Okay. Let's suppose you had 100 pages initially. It took you 1 minute to send those 100 pages. Okay. So then you will say, okay, maybe how many pages changed? Let's say 10 of those 100 pages changed. Okay. Then you send 10 pages. Okay. It's going to now take you 6 seconds as opposed to 60 because you're sending 1/10 the data. In 6 seconds, hopefully less memory would have changed than it changed in 1 minute. Because if you're assuming some rate of execution or rate of memory pages getting dirtied, your dirtying rate would result in fewer pages. So in round 3, you will iterate. You will send again the delta from round 2. Okay. And presumably the delta will keep shrinking in size because it's taking you less and less time to take the changes from the previous round and send it in the next round. Is that clear what I'm saying? Okay. So now you will reach a point where the delta becomes very small. Okay. At that point, you are going to pause the VM, actually stop executing the VM on machine A. Okay. Quickly send that delta over. That's the last delta. Okay. At that point, because you pause the VM, okay, both memory contents become identical. There's no more changes happening. Okay. But if that delta is small, it hopefully should take you milliseconds to send a very little bit of data over, and then the memory contents are the same. They're identical. Okay. Then you simply start executing on machine B because everything is the same. If you just start executing, it will just start exactly which instruction it left off, will start from there and it will look like nothing has changed. Okay. So whole VM has appeared on a new machine without the OS knowing. Okay. And there was no stoppage. The stoppage was only when you send the last delta, which was momentary. It will not be visible because it's very small. So you're not taking a minute downtime or second downtime. You might be taking a millisecond downtime. Okay. So this is what is called live migration of a virtual machine. Okay. This is called pre-copy migration. I'll talk about post-copy in just a moment. Okay. So this is how you are going to transfer the memory contents. Okay. But then you should say, wait a minute, what about resources? What happened to the IP address? Right? The IP address of machine A is going to still stay with machine A. IP address of machine B is different from that of machine A. What if there was a web server running in there? There are lots of TCP connections. You should say, would they not stop working because now B has a different IP address? So what should we do? Okay, step 8. No, step 8 I didn't talk about, but before we do step 8, there's a step, the step that's not shown on that slide. Okay, some kind of masking. What would you mask? Okay, perhaps, but that's a better way. Yes. Okay, could you not forward everything? So that's the standard approach, by the way. If you actually moved, the only way to continue to keep the connections open is you essentially open a tunnel that is simply forwarding everything that's coming over there, and then the packets are going back. It's add an overhead, but it at least allows the clients to communicate. Okay? You could do forwarding. Okay? That's one approach. Yes? Your server was running inside the VM. You moved the VM over. Now it's running here.
But what came to the previous machine will, like, to the previous machine, the IP will can't be forwarded now.
Okay. The question is, can you forward whatever has come to a machine A to machine B? Remember, there's a hypervisor running here. Okay. All the packets come to the hypervisor first before they go to the VM. Hypervisor is like the OS. If the hypervisor knows that the VM has moved over, it will say all the packets that were actually going to that VM can be sent over. That you could do. That is not a problem. Okay? Yes?
Start forwarding to machine B, tell the switch not to send you any more data, send it only to machine B, have like a
Okay.
sequence number that says what was the last sequence number that I sent, wait until that sequence number reaches machine B before sending the free.
Okay, so you are suggesting doing something at the switch so that you can forward packets. The problem with what you are suggesting is the IP address is still tied to machine A. There are other things running here that may be receiving traffic as well. You can't simply send all the traffic of A to B because this is not that you shut this machine down. There are other things running here. Okay, so you only want to move the traffic for that VM over. Okay, so the short answer is you are going to decouple the IP address of the machine from the IP address of the VM. Okay? Because this is an entire VM, it's emulating an entire PC. It has its own logical Ethernet card. Okay? We are going to give it an IP address that is distinct from the IP address of the machine. Okay? So this machine essentially has now multiple IP address, one for the physical Ethernet card and one for each of the logical Ethernet cards on each of the VMs that run. Okay? So now the VM's IP address is no longer tied to the IP address of the machine, it has its own IP. Okay, which is completely portable. There's nothing that says it has to leave that IP address behind. When you move it over, you essentially say that now the IP address has moved with the machine. The logical interface on this machine for that migrated VM is going to assume the old IP address. Okay? And this is why you need step 8, which basically says after you move it over, the switches, your Ethernet switches have to know that the second IP address on this machine is moved over. So you are going to send what is called an ARP request, which is equivalent of unplugging a machine from one port of a switch, plugging it into another port without changing the IP address. That also triggers the same thing. So it just tells the switch, now whenever you see an IP packet for this IP address, send it out on this port as opposed to the old port. That's all it is doing. Okay? That's a detail. That's not what is the important part. What is the important part is we are no longer tying the VM to the IP address of the machine. We gave it its own because it's our entire VM. We can afford to do that now. It has its own logical NIC, network interface card. So in this case, that there's no impact at all on any TCP connection, right? They are basically going to move over immediately because the switch will just start sending all the packets onto the new machine. Okay? So everything looks the same. Okay? Network connections are moved over, socket connections are moved over, nothing has changed. Okay? Which we couldn't do in process migration because the OS and the hardware did not move, only the process moved. You don't have an IP address for a process. If you could have moved that over, but we don't have any such concept. But here we have that flexibility. Okay, yes, question.
Is it correct to say that there will be a lot of communication overhead because you're moving a complete operating system? So can it be said that it will happen very few number of times, so it's not a big problem?
Okay.
So the migration will happen very few number of times, so communication overhead is actually not a problem.
So if I understand your question, maybe I didn't fully understand your question. You are asking, if I understood it right, that VM migration incurs overhead because you're copying memory contents. You don't want to do it frequently. Is that your question? Yes. So indeed, what we have not said here is when you would do VM migration. We are simply coming with a mechanism. Okay? There's a policy that's going to say when should you do it, how frequently should you do it, when should you do load balancing. That is all external to this. Whenever the policy says I need to move some VMs over, it will trigger virtual machine migration. This is what will happen. Okay? We have not talked about policies. This is simply a mechanism. It's a building block that has to be used by something else to decide when to do it. Okay? So that's a different problem altogether. Okay. So now we'll talk about post-copy migration, which is simply an optimization. Yeah, 2 more questions. Yes.
So you're essentially saying that the machine has its own original IP address that is different from the VM, so the machine can still receive its own TCP/IP connection with its own data, and the VM in the web server instance is only moving, so the machine can still receive its own data.
Yes. So point I was making, just to reiterate what you just said, the answer is yes. But the question was, machine has an IP address. Okay? And since the VM has its own IP address and the VM moved over with its IP address, the original machine's IP address is unchanged. It can still continue to receive connection. Not only that, there could have been other VMs here which have their own IP addresses. Okay, so this machine has one physical interface with an IP address. It could have multiple logical interface, one for each VM with additional IP addresses. None of those have changed. The only thing that moved was the blue VM and its IP address. All the other connections can come. You can start new TCP connections and so on.
Just a follow-up question. So because the VM doesn't really have a physical Ethernet card, does it depend on the machine's hardware, or it just gets the...
Yes. So the question is, since the machine does not have a physical card, does it depend on the actual machine's card? Yes. Just because your logical interface doesn't mean you can start sending packets without a physical interface. You still have to send packets on the network. So what is simply happening is the logical Ethernet card is physically mapped onto the physical interface. Whenever you send a packet, it actually gets sent out to the physical interface. Whenever a packet comes in, based on the IP address, it's delivered to the right Ethernet, logical Ethernet card. That's all that is happening. Yes, question.
Wouldn't there be downtime between step 5 and step 7, even if this time takes?
Wouldn't there be downtime between step 5 and step 7? Yes, I said that that's the last delta you said. I'll show you a picture of that downtime, and that's going to be a small downtime, which is almost invisible. If the delta is very small, the amount of state you want to transfer is going to be small. It'll take very little time, so then you can resume quickly. This can't be, it's not instantaneous, but there will be a very small downtime.
Even starting a VM takes time, because it's essentially booting up a full new OS on another. That happens.
This is not going to start the VM. It's simply resuming the VM where it left off, because it's already a running VM. You've not restarted the VM. You're not copying the disk image of the VM. You're copying the memory contents of the VM. Because executing OS with executing processes, they simply continue to execute somewhere else. You never rebooted anything in this case, right? If you're starting it from scratch, yes, there would be a downtime. We are not doing that. We just suspended it at some point, and then very short while later it resumes execution, not reboots. Okay? There's some other question, yes.
So what about the network communication between step 5 and step 8?
What about the network communication between step 5 and step 8? That's a good point. The point is, what happens to all the packets that actually started arriving here while this VM was suspended and started resuming execution there? Okay? Here is where this is all going into networking world, but this is where we'll rely on TCP. Okay? Those packets will not get delivered because the VM has moved over and it was suspended. Okay? They'll get lost. Okay? TCP clients will figure out that the packet never reached. They'll time out and retransmit. When they retransmit the packet, they'll get to the right destination. Okay? So you'll still get those packets, but after a round of retransmission over to the VM. Okay? The first version of the packet is going to get lost. Yes, question?
Required we have potentially long enough retry.
Okay, so question is, does it require long enough retry intervals? Not really, because this downtime is going to be very, very short. It's going to be on the order of milliseconds. TCP timers actually are operating at a much larger time scales. Okay? And they retry multiple times, so it's not a big problem. Okay? So let's talk about the other approach. It does exactly the same thing, but uses a different way to achieve it. Okay? This is called post-copy migration. And as you will see, the difference between pre-copy and post-copy is when does the copying of the memory state occur. In pre-copying, you have to first copy the state, then start executing the VM on the other machine. In pre-copy, you will not copy the entire state. You will just copy enough state over, start executing it, and in the background, keep fetching the state. Okay? That's the main difference. As is being shown here, what will happen in post-copy migration, is you will take the VM, okay, that's executing, and you will basically, while it's executing, copy a little bit of state over that is enough for you to start executing that VM. Okay? So maybe that's a fraction of the total state. Okay? And then you simply suspend this VM and you start executing this partially copied VM. Okay? It has very little RAM that you copied over. Okay? So, and then while it is executing, you are going to start fetching data over. Okay? But often there will be a problem. It might access a page that is not yet copied over. Okay? So maybe you access page 1, it has not yet come over. So at that point, that VM will stall. You will essentially fetch that page over and then execute it. This is exactly like how virtual memory works. If you have a page fault, okay, you are going to fetch that page from disk and then execute. Here you are getting a network page fault. Okay? So you are essentially going to fault in pages that you are accessing, and in the background you will just keep copying all the pages that you are not accessing, and eventually you are going to essentially get all of the pages over, then you just delete the VM. Okay? Keep in mind that since the VM is executing on the new machine, these contents don't change anymore. So you just have to bring them over. Okay? So this is called post-copy, or copying after the fact. Yes, questions?
In practice, is that going to be slower?
Okay. So question is, does that turn out to be slower? I think the jury is out on that, because I'll show you what the two approaches look like in terms of time. Okay? One has more overheads at the beginning, other has more overheads at the end. Okay? So this is pre-copy, this is post-copy. This is x-axis is time. Okay, so essentially you will see that in here you're doing round 1, round 2 which is smaller, and so on and so forth. And now here you essentially pause. That's a short pause. You copy the page over and then you restart. Okay, so there's a short pause there. Here what you're going to do is you're going to take a quick pause, copy enough state over, start executing. It's a long phase to page in data that you're not copied over or fetch it in the background. Okay? So when you do this, there is an execution overhead, because every time you take a network page fault, you are going to stall the VM. Okay? So it will be like you're faulting a lot. Okay? But once you're cached enough of the working set, maybe that's not a problem. You can bring the rest over. So the behavior is very different. Okay? Now the main thing here is, in this case, depending on the dirtying rate, there may be many rounds. Okay? If your memory is churning quickly, as soon as you copy some data over, it is changed. Okay? Then you copy more data over. So you might send a lot of data over. So if you have to transfer 4 gigabytes of RAM, you might transfer 10 times that amount just to get it all over, because it's changing rapidly. Okay? So the pre-copy phase can be long if memory is churning quickly. There's a high dirty rate for the VM. Okay? That might impose a high overhead at the beginning. Okay? In this case, you copy each page over only once. Okay? Because the memory is no longer changing, you're just faulting it in. However, you have a performance over it. Your application is stalling more. Well, less memory copying over it, but higher performance over it. In pre-copy, there's no performance penalty at all. Okay? Application is completely moved over everything, so there's never going to have this problem. But you have a high copying over it. So it's a trade-off. There's no good answer. Depends on the application and VMs. Yes.
Hybrid systems such that you pre-copy processes that are using less.
Yeah. So the question is, are there hybrid system, or how much do you do how much of the pre-copy do you do in post-copy and run it so that there is less fault over it? That then you start seeing that you do some of that and some of this, and you combine them. It's open area of research. Okay, these are all papers that people are still writing. Yes, question.
How do you decide how much is enough to restart it?
Okay, that's a good question. Question: how much is enough to restart it? So you have to move all the registers over. You have to move at least a few OS pages over, and everything else can be paged in. If you don't have registers, you can't execute anything, right? So you have to take the registers, maybe the pages, the program counter is pointing to few OS pages. Yeah, so that is good enough. That's a rough answer to your question. There are more details that depend on hardware architectures and so on, but that's basically what happens. Yes.
Usually programs have temporal or spatial locality. Can you use that to predict which page you're going to use?
Yes. So the question, that's a good question. The question is, programs often have spatial and temporal locality of references. Can you use that to intelligently figure out what to prefetch? So your post-copy phase can use all of those optimizations. You don't have to just go from 1 through n. You can say, where is this programs that are executing? What were their working set? Okay, so you can essentially get the working set first and then get the rest. So you basically, that just changes the order in which you do these post-copying. And every time you find a better order, you are going to write a new paper. Right? So that's how things actually work. All right. Any other questions here? We're out of time. We'll take one more question. Yes. Where are you seeing this? Oh, no, non-memory VM state. That just means to copy register states. Yes, you essentially have to move minimally the register and a little bit of memory. Okay. Okay. So we will stop here. Just to remind everyone, I announced this at the beginning. Lab 1 coming out today. Next week, no lecture on Tuesday, which is a virtual Monday, but there is a lecture on Wednesday, which is a guest lecture on cloud computing. Okay? Guest lectures are not optional; they're still part of the course. So don't just say I don't have to go. Okay.